Right now, over your head, there are more than 9,500 active satellites orbiting Earth. They're managing a $1 trillion industry that touches nearly every aspect of modern life. Yet most people have no idea how it actually works. These aren't just communication devices floating in space. They're part of an interconnected infrastructure that handles everything from your morning GPS directions to global financial transactions worth hundreds of billions of dollars every single day. What's remarkable isn't just the number. It's how quickly this transformed from a Cold War technology race into the backbone of the global economy. In this video, we'll explore how this industry actually operates, what these satellites do that keeps civilization running, and why companies are now planning to launch tens of thousands more in the next decade. When the Soviet Union launched Sputnik 1 in 1957, it weighed 83 kilograms and did one thing: transmitted a simple radio signal. The entire satellite industry for the next 3 decades centered on government projects, military reconnaissance, scientific research, and experimental communications. By 1990, there were roughly 300 operational satellites in orbit, and the idea of private companies profiting from space infrastructure seemed distant. The industry's economic model was straightforward. Governments funded launches, governments owned satellites, and any commercial applications were secondary. A single satellite could cost upwards of $500 million to build and launch. The technology required massive ground stations, specialized equipment, and enormous capital investment that only nation-states could afford. The shift began in the late 1990s with the commercialization of GPS technology and the rise of direct-to-home satellite television. But the real transformation came in the 2010s when private launch companies, particularly SpaceX with its Falcon 9 rocket, dramatically reduced the cost of getting payloads to orbit. By 2021, launch costs had dropped from roughly $65,000 per kilogram to as low as $1,500 per kilogram on rideshare missions. This cost reduction opened entirely new business models. According to industry analysis from the Satellite Industry Association, the global satellite industry generated $281 billion in revenue in 2022, with commercial applications representing 77% of that total. Ground equipment, the receivers, terminals, and infrastructure that actually use satellite data, accounted for $138 billion alone, more than the satellites themselves. The satellite infrastructure operates across 3 distinct orbital regions, each serving different purposes. Geostationary orbit sits 35,786 kilometers above the equator. At this altitude, satellites complete one orbit every 24 hours, matching Earth's rotation, which means they appear to hover over the same spot on the ground. These satellites handle most television broadcasting and a significant portion of weather monitoring. They offer massive coverage. A single geostationary satellite can see roughly 42% of Earth's surface. But the enormous distance creates signal delay. A round-trip transmission takes about 240 milliseconds, which is noticeable in real-time communication. Medium Earth orbit, between 2,000 and 35,000 kilometers, hosts the GPS constellation, along with Europe's Galileo system, Russia's GLONASS, and China's Beidou. GPS alone consists of 31 operational satellites maintained by the U.S. Space Force, positioned so that at least 4 are visible from any point on Earth at any time. Each satellite carries atomic clocks accurate to within 40 nanoseconds, transmitting timing signals that ground receivers use to calculate position through triangulation. The precision is remarkable. GPS can determine location to within 30 centimeters under optimal conditions. Low Earth orbit, below 2,000 kilometers, is where most of the current expansion is happening. Companies like Starlink, OneWeb, and Amazon's Project Kuiper are deploying constellations of thousands of satellites in this region. The lower altitude means signals travel faster. Round-trip latency can be as low as 25 milliseconds, making real-time applications like video calls and gaming feasible. But satellites move quickly relative to the ground, crossing the sky in minutes, which means you need many satellites working together to maintain continuous coverage. The satellite industry divides into several distinct economic sectors, each generating billions in annual revenue. Communications represents the largest segment. This includes everything from maritime and aviation connectivity to rural internet service. As of 2023, Starlink operated over 5,000 satellites, providing internet service to more than 2 million subscribers across 60 countries. The company charges between $110 and $500 per month, depending on the service tier, generating estimated annual revenue exceeding $1 billion and growing rapidly. Earth observation constitutes another major sector. Companies like Maxar Technologies, Planet Labs, and Airbus Defence and Space operate satellites that capture imagery with resolution down to 30 centimeters per pixel. This data feeds into applications ranging from agricultural monitoring, tracking crop health across millions of hectares, to disaster response and urban planning. The Earth observation market was valued at $4.3 billion in 2022 and is projected to reach $10 billion by 2030. Navigation services, while often provided by government constellations, generate enormous downstream economic value. A 2019 study by the U.S. National Institute of Standards and Technology estimated that GPS alone generates $1.4 trillion in economic benefits since its introduction, with current annual benefits exceeding $90 billion across transportation, agriculture, surveying, construction, and finance sectors. Financial markets use GPS timing signals to timestamp transactions with nanosecond precision, essential for high-frequency trading and fraud prevention. Scientific and climate monitoring represents a smaller but crucial segment. Organizations like NASA, ESA, and NOAA operate satellites that measure atmospheric composition, sea level rise, ice sheet dynamics, and ocean temperatures. These missions cost hundreds of millions each, but provide data that informs climate policy affecting trillions in economic decisions. Beyond the satellites themselves, the industry requires extensive ground infrastructure. Ground stations, facilities with large dish antennas that communicate with satellites, number in the thousands globally. Amazon Web Services operates 34 ground station facilities worldwide, allowing customers to schedule satellite downlink time by the minute. These facilities eliminate the need for organizations to build and maintain their own ground infrastructure. User terminals, the equipment that consumers and businesses use to connect with satellites, represent a massive manufacturing sector. Starlink's user terminals, for example, contain phased array antennas with over 1,200 individual antenna elements that can electronically steer their beam to track satellites overhead without mechanical movement. The company manufactures these terminals at scale, reducing costs from roughly $3,000 per unit in 2020 to under $600 by 2023. The data processing infrastructure is equally significant. Modern Earth observation satellites can generate terabytes of imagery daily. Companies like Satellogic and Planet Labs have built cloud-based platforms where customers can access satellite imagery, run analytics, and integrate data into their own applications without downloading massive files. This data-as-a-service model has opened satellite capabilities to smaller organizations that couldn't previously afford satellite operations. Operating satellites presents engineering challenges that directly impact the industry's economics. Orbital debris has become a primary concern. NASA tracks approximately 27,000 objects larger than 10 centimeters in orbit, but estimates suggest there are over 130 million objects larger than 1 millimeter. At orbital velocities of 7 to 8 kilometers per second, even paint flecks can damage satellites. The collision of an Iridium satellite with a defunct Russian Cosmos satellite in 2009 created over 2,000 trackable debris fragments, some of which remain in orbit today. New satellite operators must now plan for end-of-life disposal. The Interagency Space Debris Coordination Committee recommends that satellites in low Earth orbit deorbit within 25 years of mission completion. Modern satellites include propulsion systems to actively deorbit, burning up in Earth's atmosphere. This requirement adds cost and complexity, but is necessary to maintain the orbital environment. Spectrum management presents another constraint. Radio frequencies are limited resources regulated by the International Telecommunication Union. Satellite operators must coordinate frequencies to prevent interference, and prime spectrum allocations, particularly in the Ka band and Ku band used for satellite internet, are increasingly contested. The FCC in the United States alone has processed applications for nearly 60,000 satellites from various operators, though many of these applications may never result in actual launches. The satellite industry's current trajectory differs markedly from terrestrial infrastructure development. While laying fiber optic cables or building cellular towers requires extensive ground infrastructure and rights-of-way negotiations, satellite coverage can extend to areas where ground infrastructure is economically unfeasible. This characteristic makes satellites particularly valuable for maritime communications, aircraft connectivity, and service to remote regions. However, satellites face competition from advancing ground-based technologies. 5G cellular networks are expanding into rural areas previously served only by satellite. High-altitude platform stations, solar-powered drones or balloons operating in the stratosphere, offer some satellite-like coverage capabilities at potentially lower costs. The economic advantage of satellites persists primarily in areas where no other infrastructure exists, or where coverage must span vast oceanic or polar regions. New satellite categories are emerging. Companies like Apple have integrated satellite connectivity directly into smartphones, allowing text messaging even without cellular coverage. This required partnerships with satellite operators like Globalstar, which upgraded its constellation to handle these low-bandwidth emergency communications. The technology demonstrates how satellites can serve as backup infrastructure rather than primary connectivity. The satellite industry's significance extends beyond its direct economic value. Modern supply chains depend on GPS for logistics coordination. Shipping companies track containers across ocean routes, coordinate port operations, and optimize delivery schedules using satellite data. The global supply chain represents approximately $24 trillion in annual economic activity, much of which relies on satellite-enabled tracking and timing. Financial markets require precise timing synchronization across exchanges worldwide. Stock markets use GPS timing to timestamp trades and maintain market integrity. A 2020 analysis suggested that losing GPS would cost the financial sector approximately $1 billion per day in disrupted operations. Weather forecasting, which informs decisions affecting agriculture, aviation, disaster preparedness, and energy management, depends substantially on satellite observations. NOAA operates 5 geostationary weather satellites and multiple polar orbiting satellites that provide the atmospheric data feeding into forecast models. These forecasts influence economic decisions worth hundreds of billions annually. Climate monitoring satellites provide the long-term data series essential for understanding climate change. Satellites have continuously monitored Arctic sea ice extent since 1979, measured sea level rise with millimeter precision, and tracked greenhouse gas concentrations globally. This data informs climate policy affecting energy infrastructure, coastal development, and agricultural planning, representing trillions in long-term economic decisions. While the satellite industry has become integrated into global infrastructure, several limitations constrain its capabilities and future development. Satellites cannot provide unlimited capacity. Physics constrains how much data can transmit through radio frequencies over a given area. As more satellites launch and user demand grows, spectrum congestion will require more sophisticated techniques to maximize capacity. This represents a fundamental ceiling on how many users satellite internet can serve simultaneously in a given region. The cost reductions achieved through reusable rockets have limits. While launch costs have dropped dramatically, satellites still require specialized components that must withstand launch vibrations, operate in vacuum and extreme temperatures, and function without maintenance for years. These requirements prevent satellite costs from dropping to consumer electronics pricing levels. Satellite infrastructure cannot replace all ground-based systems. Terrestrial fiber optic networks offer vastly higher bandwidth capacity than satellite connections. A single fiber optic cable can carry terabits per second, far exceeding what any satellite constellation can provide. Satellites excel at coverage, not capacity, making them complementary to ground infrastructure rather than a replacement. The satellite industry has evolved from a government research project into a trillion-dollar infrastructure that underpins global communication, navigation, and Earth observation. The systems operating overhead right now handle everything from your phone's location services to weather forecasts, shipping logistics, and climate monitoring. What questions do you have about how satellite technology actually works? Drop them in the comments below. If you found this breakdown of the satellite infrastructure valuable, subscribe for more detailed explorations of the technology systems that shape modern life. All visuals in this video are illustrative and created for educational purposes, based on proposed engineering concepts discussed in scientific research and official space agency publications.